So we're going to narrow ourselves down to just second order differential equation, constant coefficients, linear. And we were solving for these types of problems where f of x was some particular type of function. It was either a polynomial, an exponential, or some sine or cosine. And it turns out that if the function is one of these special types of functions, then we can use the method of undetermined coefficients. And the main idea behind there is because the derivatives of these are pretty simple. Derivatives of polynomials and other polynomial. The derivative of the exponential is itself with some constants hanging outside. And the derivative of sine is cosine, the derivative of cosine is sine, or some negative somewhere in there. But in any case, the derivatives of these functions kind of remain within their particular set of functions. Now, if you start including more complicated types of functions like the tangent function or e to the x squared, it's an exponential function, but it's composed with a polynomial second degree. When you start including those types of functions, our undetermined coefficients method isn't going to work anymore. So what we need to do is we need to introduce another method, and the new method is called the variation of parameters. So for functions that are simple enough like this, we can use method undetermined coefficients. And then for other things, we need to use this new method. And this new method will work for these other types of functions as well, except they're more general and they can work for any type of function that we have. So the method is called variation of parameters. All right, how do you do variation of parameters? Let's see. Well, this is kind of long-winded here. So as a step-by-step process, we'll take a look at the step-by-step process and then see if we can come back and try to justify this whole idea. But we first look for our, that's why they call it y sub c. They call it a complementary solution. Call it y sub h last time. But first we look for the solution for the homogeneous differential equation, pretending that f of x was equal to 0. And then so that's easy enough to do, second order. So we have 3 cases for that. And then, yes, I don't know. I just copied it from the book. I'd say it's a linear combination of your fundamental solution set for the homogeneous differential equation, but they call it complementary. So you have your y1 and y2, they're linearly independent. And then what you're going to do is you're going to set up a Wronskian. So the Wronskian between the y1 and y2, we'll call that w. And then that Wronskian is, remember, the determinant of the 2 by 2 matrix that has those functions and its derivative. The 2 functions are in the first row and its derivatives are in the second row. And then what we're going to do is we're going to make sure that we write your differential equation in standard form, and we're going to identify the right-hand side of that equation, that's f of x. And then that f of x will have, if we had any constants next to the y sub 0 or y double prime, then we want to make sure we divide that out. And then we're going to create two more Wronskians, W1 and W2. And the two Wronskians will have the components of 0 f of x in whatever column that we're talking about. So for W1, we'll replace the first column with 0 f of x. For W2, we'll replace the second column with 0 f of x. And then what we're going to do is we're going to create the functions between the Wronskian, the W1 and W2, the modified Wronskians. And then we'll create two new functions. And the two functions we'll call U1 prime. And then we're going to integrate that to get the original U1 and U2. And then our particular solution then will be given by the combination of the U1 function that we just found times the Y1, the first fundamental solution, and then we'll take U2 times Y2. And that will be your particular solution. And in the end, we'll string it up with the first set of solutions that we found. Okay? That's the plan, that's the idea. Let's take a look at some examples, and then let's backtrack and figure out why this thing might have a chance of working. What? Well, we'll take a look at the proof. I don't know about cover the proof. And you're more than welcome to, of course, it's in the book. Yeah?
Looks like the method of taking inverse of matrix, which includes separate determinants. But there are easier ways of taking the inverse of matrices. Are there also easier ways of doing this?
It's not quite the inverse of a matrix. It's something else. Does this look familiar? Like, say, from yesterday's lecture? What? It's Kramer's rule. So it turns out that there's a system of linear equations that we're looking at. And the system of linear equations can be solved using Kramer's rule. And this is essentially Kramer's rule. Yeah?
Normally, when I have a system of linear equations, what you're doing with row reduction or something, does that not work here?
Well, the thing is that we have a bunch of functions that we're dealing with. It's not just numbers. And so because we're dealing with functions, the row reduction might get a little bit more complicated than it should. Okay? So Kramer's rule is this cumbersome method of trying to solve a system of equations where you have constants in the matrix, and way easier if you do row reduction. But for dealing with functions like this, it might be safer to use Kramer's rule. All right, so now that we have all the stuff laid out, I think the next thing to do is just to do a couple of examples, and then we'll see how this actually works out. So let's pick an example. Let's try number 2 maybe. I mean, we could try number 3. Number 3 you can solve with undetermined coefficients. So let's try something that we can't solve with undetermined coefficients, like the tangent. So we see that the left-hand side looks like it's a simple case of doing your auxiliary equations and stuff like that. So that seems simple enough. And the right-hand side has a tangent involved in it. So let's so we can't use the undetermined coefficient, so we'll use variation of parameters. So let's start off by finding the solutions to the homogeneous portion. So let's do a double prime, y double prime plus y is equal to 0. your auxiliary equation is m squared plus 1 is equal to 0, and so you have plus and minus I, some complex conjugates for your solutions, and so this will be sine cosine combination. So y1 is equal to cosine x, and y2 is equal to sine x. E to the 0 attached in the beginning, but that's equal to 1. So here's our fundamental solution set, and y sub c, the complementary, or y sub h, the solution to the homogeneous will just be c1 cosine x, c2 sine x added together. But let's worry about that later. So now we have this in the form where y double prime has a coefficient of 1, and so we have our f of x is equal to tan x. Okay. Now, what else do we have? We have, so we need to figure out a couple of things. We need to figure out our y, or our w, our original Wronskian. So let's figure out our w, and that's based on our fundamental solution set. So we'll list the cosine and the sine, the numerators, and then we'll need to take the derivatives. Derivative of cosine is negative sine, and derivative of sine is positive cosine. And then when you find the determinant of this, it's going to be cosine squared plus negative sine, or minus negative sine squared x, and that's just 1. So that's always nice when your w is a constant. Okay, so now we found the Wronskian. Now let's take a look at the modified Wronskians that we need. We need to find W1 and W2. So our W1, remember, is the original Wronskian, except on the first slot, we'll have a 0 f of x. Right? And then in the first column, we have sine and cosine. The second column stays the same. All right, so we get 0 minus, this is tan x times sine x. So what's tan x times sine x? Sine is, so sine squared over cosine. Oh, let's just leave it like this for now. And then the W2 will have the same columns for W, the same first column, and the second column will change. So the first column is cosine x, negative sine x. And then the new column would be a 0 and f of x, which is tan x. And then that's a cosine times tangent. And the tangent is sine over cosine, so let's just call it sine x. Okay. So now we get to define our u function through its derivative. So the derivative of u1 is going to be w1 over w. So we're eventually looking for u1 and u2. We're going to first look at the derivative of u1. So this is equal to minus tan x sine x. So if I know the derivative, I can just take the antiderivative to get the original u function. So that's the antiderivative of tan x. So this is probably where I want to write it as sine squared x over cosine x. See if I can simplify or work it out somehow so I can have a nice derivative. Is this a nice derivative? No. So I have to split this up. So it looks like 1 minus cosine squared x over cosine x. Oh, that'll work. So this is all right. Now, what happened? Where was I? So why don't we just continue on this way? There's a negative sign out here, or I could switch the negatives or whatever. So we have the integral of 1 over cosine x minus cosine squared x over cosine dx. And I think this is going to be secant x minus cosine x dx. So secant is one of those derivatives that, or integrals that you should probably try to remember. Let's see if I remember it. Secant x, tan x, ln. So I think this is equal to the ln of secant x plus tan x. And then the cosine, the antiderivative cosine, let's make sure we keep track of the negative. So that's a negative out here and a negative, so that's a positive. The integral of cosine is positive sine x dx. Oops, no more dx. So that's u sum 1. The c here would, we don't care about it. It'll get tacked on. So what if you really wanted to look at it, you should put a plus c here, and when we work things out, you'll see that it all just gets merged into the original complementary solution. So we got the u1 should be minus. So the negative here and then the negative here would make it positive, right? And then the integral of cosine is that positive or negative? Positive. Okay. You have to write that down in your sheet of notes. I always forget. Like derivative of sine is what? Derivative of sine is positive cosine, right? The antiderivative is negative cosine. I don't know. just it's the derivative and integrals of sines and cosines that get mixed up. So just whenever you're doing this, especially in the test situation, you're taking an integral of sine or cosine, just stop for a moment and make sure you're doing it correctly with a negative sign. Okay, in class, I'm just going to do it, and then somebody's going to catch me and fix it. When you guys are in the test situation, you have to stop yourself and fix it yourself. All right. This one, I think it's a little bit easier. Our u2 prime is w2 over w, which is equal to sine x over 1. So the antiderivative of this is negative cosine. So u2 is going to be negative cosine x. All right. I think we have our particular solution. So y sub p, remember it's equal to, well, I'll write it out, u1 times y1 plus u2 times y2. So y sub p includes the y1 and the y2 that we got. So that is to say that we have a minus ln of secant x plus tan x plus sine x. And all this is going to be multiplied by your y1, which was cosine. And then we have a plus, and then our u2 is negative cosine x, and then our y2 was sine x. So let's see if we can label this all U1, Y1, U2, Y2. And now we could do some simplifying as well. We have a negative cosine ln of secant x plus tan x. And then we have a negative positive sine x cosine x. And then we have a negative cosine x sine x, which will cancel. So it turns out that that thing goes away anyways. And so your y particular is going to just be negative cosine x ln of secant x plus tan x plus. Okay. And then to wrap it all up, our general solution for the original differential equation is going to be, it's going to have those arbitrary constants, a C1 times cosine x plus C2 times sine x. That's the solution to the homogeneous part. And then you have your y sub p, and that's minus cosine x ln of secant x plus tan x. Here we go. All right. Any questions? Yes.
Plus c, and then you try to actually find those coefficients, and you end up always having to completely c ended up 0.
Not that it would end up being 0, but if you were to keep that plus c here, wherever that was, plus c, and then that would be a plus c here, and then that would be a plus c multiplied with your cosine, and then that would kind of just merge in with this plus c. Yeah. And then if you do that with the sine, you do that with this one, you get the same result. It would merge with this c. Okay. Any questions? All right, let's try another one. So this one was kind of nice because the original Wronskian was just 1, but in general, it's not going to be like that. And in general, you'll have to take integrals of some weird functions. Like the secant was the weirdest here, but you know it could get kind of weird later. Let's try another problem. There's a secant squared here. Oh, we haven't done initial conditions in a while. We could do another one with a cosine squared or e to the 2x, or we could do one with initial conditions. What do you guys think? Oh, let's do number 9. Because I'm looking at this, some of this we could do with undetermined coefficients, right? Like even number 19 we can do with undetermined coefficients. So let's do one where we use variation of parameters, where we have to use variation of parameters. All right, let's try number 9. Okay, so we got our homogeneous solutions to be e to the negative 2x and e to the positive 2x. Right? You guys should be able to do this quickly now. You think? I have a worksheet for you guys to work on. I don't want to spend class time on it though, so. By the way, I finally looked at those videos that you guys made. They were pretty cool.
Yeah.
I don't know. I like them. So I think we'll do that again. Kind of fun. No, it's for extra credit. You don't have to. It's like like 5 of you guys did it. But those 5s that I saw were really cool. Yeah.
For differential equations, after the midterm, you let us do a reflection for 5 points extra credit.
Oh, I didn't do that. Wait, this is differential equations.
Yeah. Wait. Oh, shoot. Linear algebra. Never mind.
Did I not? I did do it for linear algebra. Okay, yeah, I'll do it. Okay. All right, I may ask you to email me about that.
Okay,
So, all right, we found our y1 and y2. Let's work on the Wronskian. Our Wronskian. The original Wronskian would be based on these 2 fundamental solutions that are linearly independent: e to the minus 2x, e to the positive 2x, and we get some extra constants popping out. And then the this is going to be another constant. I wanted one that wasn't constant. Oh well. So this is e to the, you add the powers, negative 2x plus 2x, and that's going to be 0. So that's just going to be 1 minus negative 2 times the same thing is equal to 4. So I wanted a function there to make our integral a little bit more complicated. Oh well. Not that this is going to be a piece of cake, but we happen to be getting solutions that are constants, and they're not always going to be constants. All right, let's find out our W1. We'll keep the W2 portion the same, so that would be e to the 2x, 2e to the 2x. The second column remains the same, and the first column will change to 0, and then whatever our function was. So that's e to the 2x over x. And so this is going to give us a 0 minus, looks like e to the 4x over x. That doesn't look like an easy integral. Trying to think how to integrate that now. I'm going to stretch your Calc 2 integral skills here. All right, we'll worry about that in a minute. Let's figure out what W2 is, and hopefully this will be easier. We got e to the negative 2x, negative 2e to the 2x. The first column remains the same. Our second column changes to whatever f of x was, e to the 2x over x. And then we have, again, e to the negative 2x times e to the positive 2x. That's going to give us a 1. And then, so this is just going to be 1 over x. Let's integrate W2 first, because it's easier. U2 prime is equal to W2 over W, and that's equal to 1 over x over 4. And because our W is equal to 4, and so that's just, let's pull the 1 over 4 out, and then ln x plus c. Wait. This is the kind of stuff that I don't like. putting equal signs where they don't belong. All right. So u2 prime is 1/4 times 1 over x, and so the antiderivative is going to be ln x. So we're done with that. Now let's think about this. u1 prime is going to be negative e to the 4x over x divided by 4, and this is going to be negative 1/4 e to the 4x over x. How are we going to integrate that? I was trying to think about how to integrate this while I was talking, and I can't come up with anything. It'll probably have to be integration by parts, right? But then you're going to have a, yeah? I don't know. What? As an integral? I would say that's okay sometimes. I don't want to quit on this just yet. No, I could. Or I could just punch it into Wolfram alpha. So what's happening? You say it's... Oh, just without having computed it? Yeah. Well, I guess we have to leave it as a... All right. So, oh, because I meant to say 4. So for something like this, I guess we'll just have to leave it. And then what's that going to be? That means our particular solution is going to be, and this is a little tricky because you want to make sure that you have x in the denominator, so that's a 0. Because the antiderivative, general antiderivative would generate a constant, but we don't want the constant to be sitting out in front. And so, I mean, the constants are coming up with our other function. So I think we'll just write it like this. Negative 1/4 times the integral from, I don't want to say 0, so I'll just say some value to some x. And this is e to the 4. And I'm going to change the variable because the variable x is now going to be the top limit. So this is u sub 1, and then y sub 1 was e to the negative 2x. And then plus u sub 2, 1/4 ln x times e to the positive 2x. And then when we find the general solution, then we'll just tack these on to the y1 and y2. So let's see. So our general solution, y is equal to c1 e to the negative 2x plus c2 e to the positive 2x minus 1/4 times integral from some value to x e to the 4t over t dt times e to the negative 2x. And the a will be determined by the initial condition if we have an initial condition. And then we have a 1/4 ln x times e to the 2x. I suppose we should check the back of the book. I'm afraid to check the back of the book. Where's the back of the book? Yeah.
Would you ever be able to actually check the initial condition, or would you have to evaluate it?
Well, the initial condition, if you have the initial condition that would come in, then you can find some numerical approximations. And that's, yeah. Where would the answers be? Appendix, main Lapuz, odd numbers, answers to odd numbers. What section are we on? 4.6. We skipped the section, so I think it's 4.6, and this was number 9. Uh-oh. Oh, 4.6. Oh, yeah. There's a 1/4. Was there a 1/4 in front of both of them?
Yeah.
Yeah. There's a 1/4, 1/4, and the integral one was negative. Oh yeah, we got it right. So something that's not integrable, you'll just have to write it as an integral. Okay. All right, I think we got it right then. Any questions about the work that we're doing? Looking okay? All right, let's try another one. This time let's try to do one with an initial condition. So oh, there's a third order one. Now let's do one after we do. Let's do one first with a second order. 19 through 22. Pick a number. 22. So 22 looks like we can actually do it using undetermined coefficients, because the right-hand side looks like it's just a combination of a polynomial and an exponential function. But they're asking us to do this using variation of parameters. And it looks like we should have initial conditions as well. So let me get those into our into the mix. So now let's do it. So let's find our, what do they call it again? C complementary. Let's find our complementary solution. y double prime minus 4y prime plus 4 equals 0. This is going to factor 2 and 2, negative 2, negative 2. M squared minus 4m plus 4 equals 0. M minus 2 twice. So we got multiplicity 2. We got our solution. Y1 is equal to e to the 2x, and y2 is going to be x e to the 2x. Our Wronskian, e to the 2x, x e to the 2x. This is 2e to the 2x. This is a product rule. E to the 2x plus 2x e to the 2x. So derivative of the first times the second plus the first times the derivative of the second, which is 2e to the 2x. So now I have e to the 4x plus 2x e to the 4x minus 2x e to the 4x. So we got a couple of things canceling out, and hopefully this Wronskian is correct. Look okay? I feel like I should just give you the problems and have you do it. I mean, is this helpful, watching me solve a bunch of them? Because I'm having fun, but I don't know if you are. You're just looking. It's not as fun when you're looking. All right. Let's change the Wronskian into the W1, and the first column will change to 0 and f of x. That's 12x squared minus 6x times e to the 2x. And then we have x e to the 2x, and then our e to the 2x plus 2x e to the 2x. All right, let's find our thing. We have 12x to the third. Oh, by the way, it's 0 minus, so let's put 0 minus 12x squared minus 6x, or 12x to the third minus 6x squared e to the 4x. So that's our W1. And our W2 is going to keep the e to the 2x to e to the 2x column the same. It'll change the second column to 0, and then that 12x squared minus 6x e to the 2x. So that's going to give us a 12x squared minus 6x e to the 4x. So that's our W2. So they both look kind of complicated, but if we divide them by the Wronskian, then the e to the 4x's cancel. We just have a polynomial. So our u1 prime is going to equal to this big mess over here, negative 12x to the third minus 6x squared e to the 4x, and our Wronskian is e to the 4x, so that would cancel. And I think that's going to be an easy integral. And then the u2 the u2 prime is going to be the same. Yeah, 12x squared minus 6x e to the 4x divided by e to the 4x. So they would cancel and you get 12x squared minus 6. Okay? So u1 is actually just the antiderivative of this. So divided by 4, is that right? Negative 3x to the 4th. And divide by 3. That's just 2x to the 3rd. And the antiderivative here, this would be 3, so that would be 4x to the 3rd to 3x squared. Okay. All right, so what do we have? We have our particular solution, y sub p is equal to u1 minus 3x to the 4th plus 2x cubed. And then u1 was e to the 2x. y1 was e to the 2x. And then y2 multiply with u2. u2 is 4x cubed minus 3x squared. And then x times e to the 2x. Now, suppose there's some combining here that we can do, right? We have to the 4th power, you have a negative 3 and a positive 4. So that's just x to the 4th. And then to the 3rd power, we have a 2, positive 2, and then a minus 3. And there's an extra x here. So that's negative x cubed. Okay. So our general solution looks like it's going to be c1 e to the 2x plus c2 x e to the 2x plus x to the 4th minus x cubed e to the 2x. And then let's now take a look at our initial conditions. So we want to take one derivative and then put in these values. So I'm going to leave some space here. We got the derivative 2c1 e to the 2x plus, product rule. You know what? Can I just combine this? Let's rewrite this as x to the 4th minus x to the 3rd plus 2, or c2 times x e to the 2x. So that, yeah, we just do the product rule one time. So derivative of the first, that's 4x to the 3rd minus 3x squared plus c2 times the second, e to the 2x plus the first. X to the 4th minus x cubed plus c2x times the derivative of the second, e to the 2x times 2. Okay, now let's put in some initial conditions here. The original function evaluated at 0 will give us c1 times 1 plus c2, whoops, that's 0, and then plus 0. So that's good. c1 is equal to 1. The first derivative evaluated at 0 will give us 2c1 plus, here I'm going to get a c2. Everything else will disappear. I have a c2 plus, and then this is a 0, and this is supposed to equal to 0. So when we put zeros in for x, we get a bunch of zeros, and we get a C2 left here. So let's see, this is 2C1 plus C2 is equal to 0, where C1 is equal to 1. So C2 looks like it's going to be -2. So there we have it. We have our solution. So our solution to the IVP oops, a little bit off the page here. So C1 was 1, e to the 2x, and C2 was -2 plus x to the 4th minus x cubed e to the 2x. All right. So that's it. Any questions? All right. Well, let's see if we can go through the proof of why we have to use the Wronskian. I don't think I know it off the top of my head, so I'm just going to look at the book. So when you're solving for the differential equation, you're going to come up with a system of linear equations. And the system of linear equations can be solved using linear algebra and matrices. Where are we? Right here. And because I didn't have this memorized, I'm going to need some help from the textbook. So I think the idea is that when you're trying to solve for this particular differential equation, you're going to want your solutions to be of the form of not just a regular linear combination of the fundamental solution y1 and y2, but it's going to be a mix of the fundamental solutions y1 and y2 times some unknown functions that we're going to try to find, u1 and u2. So let's see. Just kind of fudging through here. We want our solutions to be of this form. So we have our differential equation y double prime plus some function times y prime plus another function is equal to f of x on the right hand side. So somehow what they're saying is that a particular solution y sub p going to be some functions u1 times y1 plus u2 times y2, where y1 and y2 are solutions to the homogeneous differential equations. So now we want to figure out how are we going to find u1 and u2. So if this is a solution, what we want to do is we want to essentially take the derivatives of y sub p, so y sub p prime and y sub p double prime, and then put it back into our differential equation. And so instead of doing that, I'm just going to copy from the book here. This big mess. So finding the derivatives of y sub p will give us these linear combinations of functions, linear combinations with the coefficients u1 and u2. And then what we want to do is we want to identify when, because y sub 1 and y sub 2 are the solutions to the homogeneous differential equation, these things, the y sub 1 prime double prime plus p times y sub 1 prime plus q times y sub 1, there should be a y, is going to be equal to 0, so that stuff can disappear. And so what they did is they regrouped a little bit, and there was that trick that we saw in the beginning when we started to do first order linear differential equations, where we were able to take the left, or take one portion of our differential equation and identify it as a product rule of something. And so that's what happens here also. So you identify this as a product rule, and this is a product rule of y sub 1 and u sub 1 prime, because you have u sub 1 with double primes and stuff. And so you have product rules that are involved here. You're kind of going backwards from the product rule. And then you have ways to combine it. So you combine a couple of product rules, and you combine a couple of other scenarios here with the y sub, where you have p times the y sub combination of y1 and u prime, y2 and u prime of 2. And then this is supposed to equal to this, f of x. And so what we're going to do is, what they're going to do is they're going to set each of them equal to some values. And so let's see what from here, so from here they came up with, this is that linear system that I was talking about, where we're trying to solve for u1 and u2. Now, this is where we go to linear algebra. In linear algebra, if you're solving for, I don't know if I should use x and y's now. So in linear algebra, we have ax plus by is equal to something. Cx plus dy is equal to something else. Let's find the somethings. Into I just need some letters, alpha and beta. It turns out that solve for this, first of all, I want you to look at this linear algebra version and then look at the system that we're trying to solve. Pretend that x is equal to u1 prime and y is equal to u2 prime. And then you have a, b, c, d as your constants. And then you have alpha and beta as 0 and f of x. Okay, so you see the relationship between the two? So there's this rule, or this is way to solve for the system in linear algebra called Kramer's rule, where you find x and y. Those are the variables that you're trying to solve for in linear algebra. And this is going to equal to the determinant of A, the denominators for both of them. And then in the numerator is the determinant of, they call it A sub 1 and A sub 2, where A sub 1 is equal to basically the determinant of the matrix A, B, C, D, except the first row is replaced with the numbers on the right-hand side. And then A2 would be A, B, C, D, except the second row is replaced with alpha and beta. And then A is equal to A, B, C, D. Should have wrote that first. Okay, so this is Kramer's rule. And then again, I want you to look at the relationship between AX, BY, alpha, CX, DY, beta, and the variables that we're looking at here. You'll see that it should pop up. I don't know if it's immediately going to pop up, but if you stare at it long enough, maybe it'll eventually pop up. Malak? BD, yeah, sorry. Thanks, good eye. It's this same column from, okay? So you see the Wronskian pop up here. Your A matrix here is going to be Y1, Y2, Y1 prime, Y2 prime. And then imagine your W1 matrix, or your W1 determinant, and your W2 determinant to be the same as this, except you replace the first row with the first column with something, the second column with something. Okay? Yeah.
First one in zero again is
Yeah, it's looking at piecing these through things to equal to each other, and so it turns out that we're probably, I think we're looking at this one over here to equal 0, and then we're looking at this one to equal f of x, and this is the same as this, which is also equal to 0. If we're going to set it equal to f of x, right? So we want this whole left-hand side to equal f of x, and for that to equal f of x, we just want this thing to equal f of x and everything else to be equal to 0. Okay. All right. So I wanted to do one more example, and maybe there's not enough time, so maybe I'll just start it and then have you guys figure out the rest of it. And it turns out that this Kramer's rule works for more than just 2 variables. It can work for 3 variables. So we can also attack a third order differential equation. Wait. Here's for a third order differential equation. We can generalize to any order differential equation for that matter. But for the sake of doing things by hand, it's probably just safest to go no more than 3. So let's get another example started. And these ones look like they're third order. So let's take a quick peek at, say, number 25. All right, so this third order differential equation, so we should be expecting 3 fundamental solutions for your homogeneous differential equation. So we got y triple prime plus y prime is equal to 0. Your auxiliary is going to be, I think this is m. M squared plus 1 is equal to 0. So we have m is equal to 0 and m is equal to plus or minus I. And that's going to give us a solution. Yeah, so let's call this y1, and this is e to the 0 power. And then y2 and y3 will be a combination of sine and cosine. Okay? So in creating your matrix, you're looking at a Wronskian, a 3-dimensional matrix now. 1 cosine x, sine x, and then derivatives. So this is a third order, so we should expect to be computing like 3 derivatives or 2 derivatives. Derivative of cosine is negative sine, and then negative cosine again. Derivative of sine is cosine, and negative sine. And so you can figure out the determinant here. Let's just let's do, since we don't have time, let me just do Wronskian, the second Wronskian. And the second Wronskian is going to keep the first and third columns the same. And then the first column will be zeros and then the function tangent x. So zeros in all those derivatives, and then it'll just be a tangent in that one slot in the bottom. And so you can figure out what W1 and W2, well, this is W2, and you figure out what W3 is equal to. And then your task is to find the determinant of a 3x3 matrix, which hopefully you can do. If not, Google it. All right? All right. So there's going